Ladies and gentlemen, it's a pleasure to welcome Tomohide Terasoma from Tokyo, and he'll talk about Brown-Zagier relations for associators.
Thank you for introduction. Thank you for introduction. Today I want to talk about Brown-Zagier identity or Brown-Zagier relation and the story of Brown-Zagier relation is like this. So there was a long-standing conjecture that the map from the motivic Galois group to the automorphism group or fundamental group of P1 minus 01 infinity is injective. That is a long-standing conjecture, and it was proved by Brown. And the key point is there are many key points, but one of the key points is that there is a certain relation between multiple zeta values. It is really multiple zeta value, and that is proved by Zagier. So first I want to talk about motivation. So Zagier, I will give exact formula, and he proved certain relation of multiple zeta values, and using this relation, Brown proved the same relation holds relations hold for motivic multiple zeta value. And this is the very first step of his proof for inductive procedure. This is the very first step for proving this injectivity conjecture. And today so the next the situation is like this. Let mixed state motives over Z. Let MTMZ be a category, Abelian category, Tannakian category of mixed state motif over Z, and consider a Tanaka fundamental group phi 1 of this one. Then there is a natural map from here to automorphism group of pi 1 of P1 minus 01 infinity. So the conjecture is this is injective or not, and actually this is injective. This is proved by Brown. And but this is far from subjective. But there is a very small group, Grothendieck-Teichmüller group here, and this is it is one can show that this group, the image of this group is contained in Grothendieck-Teichmüller group. So next question is this is phi. Is phi surjective? This is next question. And by say computer experiment, it is very likely to surjective so far. So maybe many people conjecture that this is surjective. Now, what is the meaning of this surjectivity? Surjectivity means how to say, very vaguely speaking, there are many. The associator is defined certain relation called associator relation, and associator relation. This is GT is defined by associator relation. So the next question is associator relation is enough to define this motivic multiple zeta value. So the surjectivity is equivalent to using this motivic multiple zeta value. The surjectivity is equivalent to the following statement: for any relation or linear relation, Q linear relation of any Q linear relation between motivic multiple zeta value is satisfied by any coefficient of associator. So I will give the picture of this statement, the relation between this statement and this statement. So that is so very big problem. And this honestly speaking, his Brown's identity is used to showing that this image is enough big. Image of this map phi is enough big, and he proved linearly independentness of this certain element in this image. And so this relation controls how to say image of estimate from this identity estimate from below. Estimation of the dimension from below. So, in this sense, it is too small part to show this part. But anyway, this is very important relation. So, it is natural question that it is natural to ask that this Brown-Zagier relation is first proved for real multiple zeta value, and next it is proved for motivic multiple zeta value. But now my question is, any associator satisfy this Brown-Zagier relation? So any associator, coefficient of associator satisfies associator, quotient of associator satisfies Brown-Zagier relation. So this is question. Today the answer is so yes. We can prove that this equality for any associators, and actually the proof is this is one I will give the exact statement and I will give the proof. But if you look the proof, you see that this method is very, how to say, universal. It is applied to many situations. So this is one example, but many relations are obtained in our method.
Sorry?
Yeah.
So it's not known that these relations are a consequence of double shuffle. Otherwise, it would be.
Yes. That is. Actually, I don't know. Anyway, conjecturally, double shuffle relation, regularized double shuffle relation generate all the relations.
Photoshop proof that if they were in double shuffle, then they would be.
Yes. But I don't know. I don't know. Do you know?
I don't think so.
I don't know. Maybe logically speaking, it is possible.
Yeah, look,
It can be possible because conjecturally,
very possible.
very possible. But I don't know. Anyway, so how to say that? I said so. There is another group like the double shuffle, some group associated double shuffle things, and this is contained this. So if one can group for any power series which satisfy double shuffle relation, then it.
Just to answer your question, it's a whole set of equations, and you can prove something like all but one of them using double shuffle. You know one of them, you get all the others from double shuffle.
Oh.
I remember correctly.
So motivic things satisfy Grothendieck-Teichmüller also associator relation, and any associator. No. So maybe. No. So now I want to talk about these things. First, I will recall multiple zeta values and what is Zagier relation. So now, so this is motivation. And next, I will recall Zagier identity. And using this Brown's identity for this is for motivic multiple zeta value. This is Zagier's identity is proved by Zagier. This is multiple zeta values. I want to recall my convention. There are two ways of writing multiple zeta values. So my convention is same as so Green's convention, not Zagier's convention. So definition is multiple zeta values. Say Ni, N1, Nr be integer greater than 1, and Nr is greater than or equal to 2, and R is like this. For this natural number, we define multiple zeta value by this one. This is multiple zeta values. This also has iterated integral expression. This is written by like this way. This is vice versa to Brown's notation. And the first one is Nr minus 1. Last one is N1 minus 1.
So just one integral?
This is iterated integral. Integral, the rule of iterated integral is there is two way, two definition, but I adopt this definition. This is defined by omega 1x and from something to x, omega 2 omega n. And this is function of x. This is one form. So this is one form, and take the integral from something to alpha. This is a function of x. So sometimes some person write the other way around, but we use this notation. Then, so in some sense, multiple zeta value is a period integral of certain differential form on modular space of point G naught 0 curve with several marked points. Now, Zagier's theorem is like this. Zeta 2, 2, 2, 2, 2, 2, 3, 2, 2, 2, 2, 2. This is A times 2 and B times 2 here. So it is written 2A, 3, 2B for short. And this is equal to certain linear combination CAB R of zeta 2R plus 1 zeta 2, 2, 2, 2, 2. So I already said this. So this is 2 A plus B minus R plus 1. And CAB R is certain rational number, but I will not give the exact form, but this is rational number, and explicitly written using binomial quotient. So essentially, this is binomial quotient. It is very explicitly written. I can write, but a little bit long, so I will omit this quotient. This is the relation. So the weight of this is so there is a notion of weight of multiple zeta value. The weight of this is 2A plus 2B plus 3, and this is also 2A plus 2B plus so S3. Yes. And actually, this is this defines this relation. If you move this part three position, then we get many relations. And actually, this gives a invertible matrix between 2, 2, 2, 3, 2, 2, 2, and this product of two multiple zeta values. And using this relation, Brown proved the same relation. This holds also for motivic multiple zeta value. So I put here n. So. Now I want to show this. I want to show this relation for quotient of associators. So now let me give the definition of associator and several properties there are several properties. So before stating the statement, I want to give the definition of associator. First, we consider category C consisting of three objects. Three objects is like this. Like this. A very small punctured disk plus two tangential base points. This is
what's
defined by.
I didn't catch what you said. What's delta star? I didn't hear what you said. What's this thing?
This one.
Yeah.
This one is small disk. So D in C and D epsilon, where epsilon is very small. And two tangential point is some tangent vector around 0. And two is one is this direction and one is this direction. And it is known that there is two and there is this is one object. Second object is something, and it is known that one can see that there is functor by taking fundamental group, topological Bethe fundamental group and fundamental group. Object is three. There is three objects. One is this one, and next one is M04, and 6 tangential base point. Tangential base point. M04 is moduli space of. In general, M0n is moduli space of genus 0 curve with n points. This is moduli of genus 0 curve with in this case 4 points. 4 points up to isomorphism. Therefore, this is 4 point is of course numbered 4 points. Then this is isomorphic to P1 minus 0, 1 infinity. And tangential 6 tangential base point is 0, 1 for each 0, 1 infinity. There is two tangent. This one, this one. This one, this one, and this one, this one. Maybe delta. If T is some coordinate or distinguished coordinate for P1, then this one and minus this one. And if S is equal to T inverse, then delta S. Point. And around 1 it is the same. It's the same. And third object is M05. With many tangential points, 60 tangential points. We can define this tangential point in certain combinatorial way. Tangential points correspond to the planar. This corresponds to planar graph. Planar graph. Whose edge. Planar trivalent graph. Planar trivalent tree. Sorry. Planar trivalent tree whose edges are numbered by trivalent tree whose edges are numbered by 1 to 5, from 1 to 5. So altogether there is 60 tangential base points. This is one, for example, like
Binary.
this is one example. Is it okay? And so if you fix something, up to planar.
Up to reflection.
So planar means this cyclic order is fixed, specified for each.
So there's no symmetry in twisting 1, 2, or 3, 4. There's no symmetry in twisting 1, 2, or 3.
This is not equal to 2, 1.
Okay.
Cyclic order is specified.
Actually, it's not the edges that are numbered. It's not the edges that are numbered in your picture.
Edges of no, terminal. Terminals are terminal. This is terminal. I'm sorry, edge is this one. So I define object, and morphism is a little bit technical. So I want to skip the detail. But first object is, of course, identities are supposed to be object, and also delta star to M04, preserving the set of tangential base points are morphisms. This is map preserving in tangential points. So there are altogether 6 morphisms. And also the next one is a little bit technical, but M05. From M04 to M05, an infinitesimal inclusion close to boundary component. So it's it is defined by global. If you compactify this M05 and consider a normal bundle of the boundary and take a global section or rational global section of this normal bundle, then it defines infinitesimal inclusion. So, and altogether there are 120 morphisms. Anyway, it is easy to find. Anyway, this is written very combinatorial way. and composite. Of them. Of course, it is. One can define for example, the automorphism group preserving 6 tangential base point is not included in this category, but for the definition of associator, it is okay. This is sufficient. And there are two functors that we define.
Maps from the objects to themselves. Maps from M04 to M04.
It's not included in this category, but for the associated it is okay. So if we define very small category, then we get better results. So we can forget the automorphism group.
Is it obvious why there are only 6 morphisms up there, or
six morphisms?
Or what is it? 6?
6 morphism is this
The name.
punctured point go to 0 or 1 or infinity. So there is 3
Oh, I see.
possibilities.
Just the, okay.
But this change, so altogether 6 morphisms. So two functor is defined. 2 functors are defined. So one functor is consider fundamental groupoid of so any object M with the data of points. Data of base points, we attach a groupoid of M with 2 index here, and this is functor.
Excuse me, I want to make sure. The category C, the set of objects of this category C is only 3 elements.
Yeah.
So you are not taking care of the ordering of 6 best tangential best. You are not. It's just
this is one object.
just one object. You don't mind the numbering of.
So if you change the numbering, one can define another category, a little bit category which contains changing is considered as a morphism in this category, but we do not here. Maybe it is possible to make 3 objects.
3 objects.
3 objects. Yes. Only 3 objects.
I understood one object is the pair of.
Yes. Object is X and S is finite set in X finite. So how to say? Point-setted space.
Space.
Not a pointed space. Point-setted space.
An abstract category has elements which have strange names.
Point-setted space. And morphism is morphism from this to this, preserving points, tangential points. This is some set S, and this is star, and star is an element of S. So strictly speaking, groupoid is a series of set indexed by two points in S, and it is the composite is defined such and such, and associative is satisfied and such and such. That is, so this is groupoid functor. This is groupoid functor. Groupoid functor. And from this we can define multiple completion of phi 1 of this fundamental groupoid, then this is called, so Hopf algebra, or dual Hopf algebra, maybe it's better to say dual Hopf algebra. This is Hopf algebra object. And this is multiple completion of the group ring of this fundamental groupoid. So this is called fundamental algebroid over this set S.
Excuse me, this is star prime, right? This is fundamental group or fundamental total?
Fundamental group.
Is the star the same?
No, different.
Star prime.
Yes.
So it's not.
Yes. Star prime.
No. And M is delta star or M04 or M05, right?
M is delta star or M04 or M05.
And S is a tangential base point.
Yes. S is in this case 2 points, 6 points, or 16 points. This is one functor. Second functor is almost similar, but we use drum fundamental group instead of Betti fundamental group, usual fundamental group. Then second functor is M S to Q phi 1 drum of M star. Actually, drum fundamental group, it does not depend on the choice of two base points, but so it is constant groupoid. Actually, this is group, and this is group, and this is algebra. But nevertheless, we write these two base points. Start line. We have two algebroid functor, so we get two algebroid functor. The associator, set of associator is defined by phi in functorial an element in functorial isomorphism from this functor is written by U drum. U stands for universal enveloping algebra. This functor is written by U Betch. Sometimes this is very long notation, so I will write this U Betch of M. Functorial isomorphism from the functor U Betch to U drum. Functorial isomorphism is to give such that so this is the set of isomorphism. Of course, this is a set of isomorphism for any object. For any object, phi m is an isomorphism from U Betch C. U Betch tensor C. U Betch M tensor C. Tensor C is completed tensor product of with C used RAM and tensor C, such that this commute with all the morphism of given here. That is the definition of functorial isomorphism. And then for any M in object C, then and associator is functorial isomorphism which satisfies delta phi star. The condition is delta phi star. This is so log rho to C E, which sends log rho to 2 pi I E. So phi delta star is a map from this algebroid to this algebroid, but log rho is very small circle around like this, goes to 2 pi I. Rho is an element like this. Then log rho is an element in this, and this goes to 2 pi I. Of course, this is Hopf algebra, morphism of Hopf algebra. So this should commute with coproduct and product. So this is the definition of algebra, associator.
So what was your map from M04 to M05? Did you have maps from M04 to M05?
Yes.
What are the maps?
120
Yes.
maps. For example, M05 is C2 minus C minus 01 times 2 minus diagonal. This is M05. So the complement of this picture is M05. This is the complement of this picture is M05, and we compactify this in, say, for example, P1 cross P1. Compactify P1 cross P1, then we get like this.
You can send it to the M05 bar, and then what?
Yes, M05 is complement of this one.
Yeah.
So we compactify M05 so that this point becomes normal crossing. Then like this, blow up 3 points. This is M05
Yes.
bar.
Bar. Yes.
So if you consider this something like here, close to here, then we can embed. So we choose a normal bundle, normal section of normal bundle. Then we can very close embed M0. So I will write.
M05 bar is a Petzl surface.
Yes, M05. So M04 to M05 is not a morphism algebraic variety, but infinitesimal morphism of algebraic varieties.
Yeah, I mean, but you can't. I mean, you can map to the boundary divisors,
Yeah.
and then you want to move the boundary divisors in, or something like this.
Yeah.
Okay.
Boundary, yes, very close to boundary.
You're gluing it on the inside of a tubular neighborhood or something like this. Choose a global section of the normal bundle. Some way, and you glue a copy of M04 in the normal bundle. It's
Yeah, but
infinitesimal
yeah,
neighborhood.
Maybe if you
That's not clear. It's
the
a
dual
little
map.
subtle, right? Because you wouldn't have to go to the compactification.
okay. So if you want to know a very exact definition, we must think something like same symbol of local system, and it depends on the normal boundary. And
Yeah.
one can define very vigorously, mathematically.
If I can make a little bit of publicity in a book we edited 20 years ago on dessin enfant, there's a beautiful explanation of Yasutaka Hihara. He explained all of this and he proved that GQ is included in GT with Pisa series with 2 variables and so on. And Hihara, Yasutaka, he detailed all of this with Pisa series in 1 and 2 variables.
Yes,
that
yes.
GQ is included in GT by using this. So
Yes,
it's really careful. And
Yeah, no, all I'm saying is the canonical maps go to the boundary. And then you have to do
Yeah.
something.
Yes,
How
yes,
is
yes.
Sorry,
you say it's in the book?
Yeah, even
it's
then.
in the book.
But then you have
Dessin
the
enfant.
choice to move it away from the boundary.
It's in the LMS series. Hihara.
I don't realize.
You can wait here.
Yes.
Yeah, you can buy it here in the library. If you come with a letter from the news institute, you have 25.
Maybe I can what you
I think I've downloaded from the website.
Find it here.
Anyway, it's all nicely
Okay.
said by here.
Then I will give very important properties, namely three. I will give 3 properties. Fact 1 is this pi is uniquely determined. By the image of 0, 1. This is written DCH in Brown's lecture. Image of 0, 1 in the under the map in M04. You batch M04 to U drum M04 and consider 0 to 1, 0, 1 to 1, 0. There is a very standard element 0, 1, and the image of this. So image of this is phi M04, 0, 1. And this is
So let's see.
drum fundamental group of M04. So this is a C.
Tensor with C.
Yes. So this is an element in C, E0, E1. And therefore, this is an element of formal non-commutative formal power series ring of 2 variables. And so this is written as a function of E0 and E1. And I want to use the same character. Maybe it is we do not confuse because it is exactly the same of associator. So I use the same character for this element. This is called. So someone calls this element is associator, usually associator, by defined by Drinfeld. This is not Drinfeld associator, defined by Drinfeld. And second fact is.
This is a completely general associator, is that correct?
Yes. Second fact is.
Associator rises.
The second fact is this functor extends uniquely to M0n B U B of M0n to C U drum of M0n. So preserving functoriality. So satisfying functoriality. I did not define the functor extending this small. I not defined a category which extends this small category, but also we can define infinitesimal embedding for arbitrary n and n plus 1, m0n to m0n plus 1, and so on. We can define similar embedding for arbitrary number of points in genus zero count. So this fact is how this fact is many person state this fact. Yeah, for example, Ihara also states fact, and maybe you state this fact somewhere. But this is.
Isn't it Eilenberg-MacLean?
Who?
Eilenberg-MacLean?
Yes. This is essentially Eilenberg-MacLean's theorem. So, parentheses, so way of parentheses is independent if if it is compatible for 5 tensor products. 4 tensor products. 4 tensor products. No, 5 tensor products. The fact 3 is there is very important functorial isomorphism called classical comparison map. I impose this condition which satisfied by classical comparison map, and classical comparison map is comparison map from isomorphism between MC M0n to M drum C M0n, and compatible with classical comparison map is compatible with infinitesimal inclusion and infinitesimal inclusion. So this gives a certain element phi in associator, and this associator is called Drinfeld associator. So we use the same notation, and Drinfeld associator E0 E1 is in certain particular associator contained in this E0 E1. And the fact is, moreover, if you expand this formal power, non-commutative formal power series with respect to the word consisting of this 0 and 1, then if you expand this formal power series as a sum of C word or E word, W is word, including empty word. Then, so EW is, if W is word I1, IR, then EW is defined by EI1, EIR. And C omega is an element in C. A fact is that most of all the coefficients can be expressed as by multiple zeta values. So the continuation of fact 3, C of 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 is equal to zeta, multiple zeta of the zeta and zeta R. Here, N1 minus 1 here, NR minus 1 here. And since phi is associator, any associator is defined by compatibility condition for this map. Therefore, if you write down this compatibility condition, then there are many relations arise by this functoriality. Functoriality is commutativity of such relation. Therefore, if you write the commutativity of this relation, then we already know the fundamental relation of relation of moduli space of M05. This is very concrete. There is very concrete expression. Therefore, this the image should satisfy the same relation. Therefore, we write down this relation. Then we get many relations between the coefficients of associators. Associator condition relation between C omega. I will write for general associator. We write this coefficient C phi. C phi is so phi. If you expand this phi E0 E1, then the coefficient is written as C phi. I should have mentioned omega E omega. This coefficient satisfies many relations, and many. So it is many. It is expected that all the Q linear relation between multiple zeta values are obtained in this by this relation. This is so expectation. Anyway, from this, at least we can say that there are many relations for multiple zeta values. So multiple zeta values is a coefficient of Drinfeld associator. So, and the Drinfeld associator is one particular element of associator. So therefore, this relation gives many relation between multiple zeta values. So the question is then. So the question is all the rational relation comes from so how to say it is not known that up to now it is not known that all the Q linear relation between multiple zeta values comes from associator relation. It is not known, but so the surjectivity conjecture is equivalent to as I said, surjectivity conjecture is equivalent all Q linear relation come from associator relation.
All relations between motivic multiples.
Yes. Q linear relations between motivic multiple zeta values. If you change multiple zeta values, then it contains another. Problem like related to transcendental number theory. But if you write like this way, then it is in some sense combinatorial question. So theorem is theorem is this relation zeta 2, 2, 2, 2, 2, 3, 2, 2, 2, 2, 2 equal sum of zeta 2r something 2r plus 1 zeta 2 to a plus b minus r plus 1 some question holds for any associators. So I put phi here, where zeta phi n1 nr is defined by the similar given by the similar formula. So c phi of 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 is n1 minus 1 nr minus 1.
Maybe you need a factor minus 1 to r. Otherwise,
minus r.
minus 1. This is up to sign. This is up to sign.
dz over
Sign. Yes. Thank you. Okay. So I will give outline of proof. First, I will give an outline of proof, and I define a certain cohomology theory called phi cohomology. Phi means associator. So we can define a cohomology theory associated to associator. So I will give an outline of proof. First part is the same method of Zagier. First, we consider the following generating function. So Zagier's. So I want to recall Zagier's proof. This is like this. We consider generating function on this. This is n. This is m. And 2n plus 1 x to m. We consider this n m. We consider this generating function. Then Zagier's first observation is if you consider this generating function, then this is equal to sy. What is sy? Sy times this is expressed as a hypergeometric function. So hypergeometric function is function in 6 variables. First 3 there is 3 variable, 2 variable, and 1 variable, and 3 2 means this 3 2. And hypergeometric function is defined as follows. F3. So it is very concrete. A1, A2, A3, B1, B2, G. So 3 variable, 2 variable, and 1 variable. Then this is defined as A1n, A2n, A3n. This is special function, and it is very related to moduli space. This is the definition of hypergeometric function. So the equation is, this equality is sy is pi y sine pi y.
These are Pochhammer symbols. These Pochhammer symbols there.
Yes. The Pochhammer symbol is this symbol is a1 n is equal to a1 times a1 plus 1 times a1 plus n minus 1. N product of consecutive numbers. How to say? This is quite interesting. This is generating function of multiple zeta value, and multiple zeta value. This generating function can be expressed as hypergeometry function, and hypergeometry function is I wrote in this form. This is series expression, but there is also integral expression of hypergeometry function. Integral expression is something like this is also something like gamma factor here times integral of 0 to 1 2 times x to the a1 minus 1 x to the a2 minus 1 minus x1 minus a1 minus 1 minus x2 b2 minus a2 minus 1. This exponent is not so important, but maybe it is better to write to get certain image. So,
Is there no exponent for the last factor? Is there no exponent for the 1 over minus c x1 x2?
Exponential minus a1. A1, A2, S3. This is what is interesting. Maybe we use this expression to prove the Brown-Zagier identity for associators. First, we know that by this expression, there is a gamma factor, but by this expression, A2 and S3 is in some sense symmetric. But this is A2 and S3 is not symmetric. Nevertheless, so if you change this A2 and A3, then there is a identity for integrations. This is equal to some gamma factor A3 here and A2 here. So there is different. So this corresponds to, if AI is a rational number, this is a certain period integral of covering of P2 associated to this exponent. And if you change this exponent, then variety is totally different. So if you this expression implies even though different algebraic varieties, there is a relation between period integrals. So the question is why this coincidence of period integral happens. So anyway, so this trivial identity can produce very non-trivial identity on periods. So, and this identity, always this identity comes from algebraic correspondences. Many identities of hypergeometric functions comes from algebraic correspondences. This is what I want to one remark. Next, this is first thing. Second thing is the same. We consider the same generating function of the right hand side. Right hand side of this equality. Right hand side of, so already 10 minutes past, equality times y to the 2n plus 1 x to the 2n plus 1 2n. Then this becomes sum of C function. C function is CG is this is dialog function, D-log function. This is defined by dg d log gamma g. So linear combination of easy linear combination of psi function. Then the Zagier proved these two function coincide. As a function, not number, but generating function is equal. So Zagier's proof. Third part is Zagier's essential part is this generating function 1 and this generating function coincides. 1 is equal to 2. And his proof is both function is analytic on x and y, and it can be extended to a certain way, and this has the same value on integers. Therefore, these two, 1 and 2, is equal. This is the way Zagier proved, and also Lee proved another proof. This is using evaluation at integral d, and Lee proved same equality. He proved using functional equation for hypergeometric functions. There are many formula related to hypergeometric functions. Many formulas are written in Bailey. He's very old mathematician, and he wrote a book, and it is printed from Cambridge. And also elderly, and so on, and Hoyter-Watson, and so on. There are many formula, but using these formula he proved. The essential part is two formula. One formula is Selberg integral formula. Selberg integral formula is something like x1, x2, alpha minus 1, it's 1 minus x1, 1 minus x2 beta, x1 minus x2 2c dx, dy, dx1, dx2. This is expressed by product of gamma function. This is Selbag integral formula. And the next formula is contiguity relation. And so on. And this is contiguity relation and connection formula. And they are, of course, related to period integral. And also, this Selbag integral is related to period integral. And this, we can show that this also comes from algebraic correspondences. Now, I want to continue the
Excuse me.
proof. Yes.
Can I ask a question?
Yeah.
How should I think about the information content of the 3f2 function? You pointed out that associators extend to any number of mark points.
Yeah.
And this 3f2 looks a bit like a M05 object.
Yes, that's right.
Does it still know
This is still 5 object. Yes.
Does it still know about a higher number of mark points?
Yes, that is very good point. Yes, actually, from the I will write down a very interesting formula. One formula is to prove this Euler-Zagier relation. The following equality is very essential. Just a moment. Yes. I will not give the details, but the form is like this. So F32 corresponds to M05, integration of M05. F21 is related to M04. This is Gauss hypergeometric function. If you evaluate one at Gauss evaluate at 1, then Gauss hypergeometric function is decomposed into beta function. So in some sense, this is not so interesting. But if you consider this, then like this Selbag integral and so this F32 appears. But to prove it is very essential to use 4-3. The relation is like this. You need. So actually, this is related to M06. So it is very important that this associated isomorphism extends to M06. Otherwise, we cannot prove. We use in such a way. The integral of 0 to 1, F21, and something here, and variant is US here, and S2 the something, 1 minus M2 the something, F21 something, 1 minus S, and integrate from 0 to 1. Integrate from 0 to 1. Then this is equal to gamma factor times F43 something here. So this is integration over, this is three-dimensional things. This product of one-dimensional things here, and we consider new integral variable. Then if you integrate such things, then this is equal to certain u. it can be expressed as a hypergeometric function, this hypergeometric function. Therefore, and if actually to prove the Selberg integral, we must use, I don't know. Also, we must use three-dimensional varieties. This is the two-dimensional integral, but to prove, we must think to three-dimensional integral. Maybe I will, if there is a time, then I want to show. But
is there a geometric interpretation of this convolution thing, using
yes.
the fact that there's a boundary component of M06 that's M04 cross M04?
Yes. This is in some sense convolution. Yes.
Can I think of it geometrically by using the fact that there's a boundary component isomorphic to M04 cross M04?
A boundary component?
Boundary component M06, which is a product of M04 itself.
This is so. This boundary is
extending the boundary. Yeah.
But there is how to say? Boundary is fixed. So this has some exponent. This has some exponent.
Is it some neighborhood of the boundary? Is there a geometric way to think of this formula as integrating over some neighborhood of the boundary extending into?
Yes, but if you have something here, then how to say, boundary there is a regularization principle that one can define limit. How to say, limit of integral in cohomological way by using, if alpha is not contained in G, then it can be how to say, extended natural way by using monodromy divided by 1 minus monodromy. Okay. Now we want to follow to the proof is we follow Zagier and Lee's proof. So to how should I do? So it's already.
How long do you reckon will the talk go? Maybe it's a good time for a break now.
Yes.
And then we start with the talk after the break.
Yes.
Okay.
Let's take a break. Coffee time.
That's already.
Yes.